Bismillahirrahmanirrahim. I am Dr. Abir Badsha, lecturer in Department of Chemistry, Cohort, University of Science and Technology. Today, the topic of our lecture is elimination reactions. This is lecture number 15 from the course Organic Chemistry 2nd, having got chem not it is 3, not 1. It is from the course 322. The outline of our lecture will be include introduction, followed by E1 reaction, and then followed by E2 reaction, and then what are the evidences for both E1 and E2 reactions. And then we will discuss the various factor which is affecting E1 and E2. It means which factor will favor E1 and which factor will favor E2. And at the end we will mention some references from which we have taken this lecture. Let us come first to the introduction. Mostly in this case, a substrate is attacked by a base, and is a result of which an eliminated product in unsaturated saturation is produced. Here the mostly commonly used base for elimination reaction are potassium hydroxide in alcoholic form, or sodium hydroxide, or sodium ethoxide, or potassium ethoxide, sodium amide, and tertiary butoxides. These are the various bases used for the elimination reactions. In that case, this species alcoholic potassium hydroxide, or the OH, it is a base. It abstracts hydrogen from the beta position. Beta position is their position which is adjacent to the alpha, and alpha position is that one to which the functional group is attached. This is a functional group halogen which attached to this, so this is alpha, and the position to alpha, the carbon a 2 position to the alpha, then is called a beta position. So this OH which has a negative charge, it abstracts a hydrogen from this species, so it acts as a base. Here this is the positive center, and this nitrogen hydroxyl group is the negative center, so it is abstract this hydrogen, so it acts as a base. In some species, when it is aqueous form, then the OH will act as a nucleophile. It will not abstract hydrogen, but it will attack on the positive center through which the living group live. In that case, then this species will act as a nucleophile, but here it acts as a base. When it abstracts hydrogen and at the same time chlorine is also left, an eliminated product is formed, which where an unsaturation is produced. This mechanism, which is called beta elimination, because hydrogen has been abstracted from beta position. There are alpha elimination too, and there are this one is the beta, and there is another type which is also called the gamma position. If both hydrogen and leaving group abstracted from the same carbon, for example this is the same carbon and this is the leaving group and this is the hydrogen, if they are abstracted from the same position, then it is called alpha elimination. If it is abstracted from the beta position, for example from this position hydrogen has been abstracted, and from this position the leaving group leave, for example this is a leaving group and leaving group leave from here, then this is called beta. But if hydrogen is abstracted from a position which is a third position to the alpha carbon, for example this is alpha carbon having a leaving group, this is 1, 2 and 3. If it is abstracted from the third position, which is also called, this is alpha position, this is beta position, and this is gamma position, So this is also called gamma elimination. But here we will mainly focus on the beta elimination, where the hydrogen is abstracted from the beta position. So the formation of this eliminated product can be formed by two pathways. First one is the concerted and the second one is the stepwise mechanism. In the concerted mechanism, if it follows the concerted mechanism, then it is called E2 mechanism. In the concerted or in the E2 mechanism, the abstraction of proton and the departure of the leaving group, which is also called nucleofuge, and if it is take place simultaneously, then such type of mechanism is called E2. For example, here hydroxyl group abstract this hydrogen and this nucleofuge leave, and the leaving of this nucleofuge or leaving group and this abstraction of hydrogen take place simultaneously, then it will follow E2 mechanism or concerted mechanism, because it is take place in one step. The mechanistically it has been shown that the base abstract hydrogen in the leaving group leave, so there are intransition is such that the bond formation take place between the hydroxyl and hydrogen, and at the same time the bond breakage take place between the carbon and hydrogen as well as between the carbon and the leaving group, and a result we get the eliminated product along with water and the newly leaving group or nucleofuge. What are the evidences? First evidences for the formation of in the pair of E2 is kinetic. If the rate depend on both the concentration of the substrate as well as base, then it will follow the E2 mechanism. If we increase the molar concentration of the substrate, or if we increase the molar concentration of the base, so the rate of the reaction is enhanced, then it will follow E2 mechanism. In this case, both the concentration of the substrate and base involved, so it is of second order or it is also bimolecular reaction. That's why it is called E2, where E represent elimination and 2 represent bimolecular. It means two molecules, both substrate and base, are involved. So that is why it is called bimolecular, and the reaction is elimination, so it is called E2 elimination reaction. Second evidence is the stereochemical studies. Stereochemical phenomenon operate only if the substrate has more than one type of beta hydrogen. For example, this is a carbon and which has a nucleofuge, and at that position here is a carbon and here is a carbon, and here are hydrogen. Here hydrogen is present and here is hydrogen present too. Then in that case stereochemical study will be involved, that along with this leaving group this hydrogen will be abstracted or this hydrogen will be abstracted. So it is depend upon on the nature of the leaving group. If the leaving group is uncharged, when it is this nucleofuge attached with the carbon, and during this it remain neutral, like here it has no any charge, and when it is leave, and during leaving it leave is a negative charge. Here for example, if it leaves, so negative charge will be appear on it. Then in that case, which hydrogen will be eliminated? That hydrogen will be eliminated, which result in more substituted alkene, which is also called Serge product. Their product will be dominate. For example, it has been shown here that this is on charge leaving group. So when it is leave, so it will leave is a negative charge species. when it leaves is a negatively charged species. So during this phenomenon, this hydrogen will be abstracted, or this hydrogen will be abstracted. So it has been mentioned here that the more substituted alkene, it means the surface product will be the dominates. Here if we abstract this hydrogen, then the double bond will come here. So here a substitution, this is less substitution because here only one alkyl group is present. And if this hydrogen is abstracted, so the double bond will become here. So there are two alkyl group are present now along with the double bond. So this is the more substituted. So the more substituted alkene will be formed only when the leaving group leave is a negative charge. If the leaving group is charged, for example, it has been shown here, when it is bonded with the alpha carbon and it has charge, is this species is charged species, and when it leave, and during leaving this species leave as a neutral species. For example, this species will leave as a sulfide CH3, dialkyl sulfide CH3CH3. So in that case, which product will be dominate? And that product, if there are possibilities of 2 alpha, and there are here are 2 alpha beta hydrogens, in that case the less substituted alkene will be formed. In that case, if this hydrogen is obstructed, so in that case you will get this alkene which has only one alkyl group. So this is the least substituted, and the least substituted product is called half-man product. And if this hydrogen is obstructed, then the double bond will be shipped here, and this is the surface product, but the amount of the surface product will be less. So wholly solely the shifting of double bond in the eliminated product depend upon on the nature of the leaving group. If it is neutral in leave is a negative charge, then surface product will dominate. If it is a charge in leave is a neutral species, then the half-man product, it means the less substituted alkene will be dominant. In some cases, if the base here mostly as I have mentioned in the previous slide, that potassium hydroxide or sodium hydroxide or sodium ethoxide or potassium, or sometime a base of large size, for example potassium tertiary butoxide is used. In that case, if a base of large size is used, then half-man product will be dominate. In that case, the nature of the leaving group, whether it is present is a charged species or it is present is a neutral species, doesn't matter. In that case, the dominancy will be that of the half-man product. For example, it has been shown here. Here the leaving group is the charged one, and here the leaving group is uncharged one. When this group leaves, so this group is a neutral, and when this group leave, it will leave as a negative charge. But here, if we use sodium ethoxide, then what will be the dominancy here? The dominancy will be here of the substituted product. And if the sodium ethoxide is used instead of this, in that case, then the dominancy will be of the citizen product. But here, if tertiary butoxide is used, which is the base of large size, in that case, the more substituted the more dominant product will be that alkane which is half-man, which is less substituted. For example, here when this group is leave, so this tertiary butoxide will can abstract this hydrogen as well as this hydrogen, but the size is large, so it can easily abstract this hydrogen, and as a result a less substituted or have main product is formed. If it obstruct this hydrogen, so it will form this more substituted product. But here the size of the base is large, so it can easily obstruct this hydrogen, and is a result of which the less substituted or have main product will be dominant. Similarly, if the leaving group is neutral too, still the more product will be, or the dominant product will be the less substituted. Here again, here the less substituted product, and here it is the more substituted product, but the size of the base is large, so it doesn't matter if the leaving group leave is a neutral or the leaving group leave is a charged species, still the dominancy of the half main product will be more. Now let's come to the evidences of elimination reaction. We know that E1 elimination reaction or E1 mechanism. Mostly E1 mechanism is carried in two steps. In the first step, leaving group leave, and in the following step, for example, this is the species where elimination takes place. For example, this is the leaving group and this is the hydrogen. So in that case, first the leaving group leave. By leaving of the leaving group, what will happen? A positive charge will be appear on this carbon, and the leaving group will be leave is a nucleophile, is a negative charge. Then what will happen next? The base will obstruct. In the following step, what will happen? The base will obstruct hydrogen. For example, it will obstruct hydrogen from this position, and is a result of which a double bond will be created in that case. So here the rate determination step is this one, because here a carbocation is formed from the neutral molecules, the formation of a carbocation. This is a in this case we go from the stable state into the unstable state, so it is the slow step, and in this is the fast step, because here a take place and we can get the neutral product which is a stable one. So this is the fast one. In the first one there are two species involved, this intermediate in the base, and in the slow step only substrate is involved. Here this step is slow, so the rate only depend upon on the concentration of the substrate, not depend upon on the concentration of the base. So here rate only depend upon on the substrate, or rate is equal to K followed by the molar concentration of the substrate, where K is a constant which is called rate constant. Since it only depends upon on the concentration of the substrates, that's why it is called E1 reaction, where E represent show elimination and 1 represent unimolecular reaction. Second evidences of E2 is the stereochemical studies. Like E2, we know that in E2 the more substituted surrogate product dominates only when the group which leave is a negative species. Same is the case here too. If the species leave is a negative one and it present here is a neutral species, then if more than one beta hydrogen is available, then is a result of which more substituted product or surrogate product will be dominant. For example, here when this group leave, so there are two hydrogen available. This is also beta position, this is also beta position, and this one is also beta position, but these two positions are the same, so we consider only one, this one, and this position is different because here is the ethyl group and here is the methyl group. So there are two type of hydrogen, one hydrogen is that, one hydrogen is that. So base will obstruct this hydrogen or this hydrogen. So According to the experimental studies, the base will obstruct this hydrogen. Why? Because a double bond will form here, as a result of which a more substituted product is formed. It is twice substituted product. But if the base obstruct this hydrogen, then the less substituted product will be formed where there are two substituent is present. This is the Hammond product. So in this case, like E2, in E1 reaction 2, the more substituted product will be dominant. The third evidence is for the E1 reaction is rearrangement. It's mean the formation of intermediate. When the leaving group leave, so what happen? Intermediate is formed. This intermediate is the primary intermediates, because here carbon is present on the primary carbon. If there is a possibility of conversion into secondary or into tertiary, so it will rearrange. So there is a possibility when this methyl group shift from this position to this carbon positive charge, so the positive charge will be shift here, is a result of which the secondary carbocation will be formed. And then there are two type of hydrogen. One is this beta position and one position is this. So as a result, in this case, more substituted product will be formed. It means the zip product will be formed because there are more substituent. If the hydrogen is abstracted from this position, then less substituted product will be formed. But here the zip product will be dominant one. Now we are coming to the factor which are affecting the rate of the chemical, the E1 or E2. In some cases, some factor favor SN1, in some factor E1, in some factor favor SN2. What are those factors? Those factors include substrate, the nature of the base, the nature of the leaving group, and as well as the nature of the solvent. Number first one is the substrate. That what type of substrate? If we want to prepare a compound through E1, or if we want to prepare a compound through E2, so what type of substrate will be needed for that? We know that during the E1 reaction, formation of carbocation take place, and we know about the carbocation. The tertiary carbocation is more stable than secondary carbocation, and secondary is more stable than a primary, and primary is more stable than the methyl carbocation. For E1, the tertiary carbocation is needed when in a reaction the tertiary carbocation formation takes place, so it will favor E1. For example, it has been shown here. This is the it result primary carbocation, because when hydrogen is bromine is leave, so positive charge will be up here on this positive, so it will be primary carbocation. When similarly when bromine leave this carbon, so positive charge will be up here on it, it will result secondary carbocation. If bromine is left from here, so then it will result positive charge on this carbon, and that species is called tertiary carbocation. So if we move from the primary halide to secondary, or from secondary to tertiary halide, so the E1 mechanism, the E1 type of reaction will be enhanced, because in this case it will follow E1, but it will be a very least reactive. But in this case it will take place to E1, which is at a high rate compared to the primary one, and the tertiary one will react through E1 mechanism at a very high speed compared to secondary and primary one. As shown here, if we plot rate against the various carbocation, so in the for E1 reaction, for carbocation, primary carbocation, the rate will be very slow. But if we change carbocation into secondary, so then the rate will be enhanced, and if from secondary change to into tertiary, the rate will be further enhanced. Second one is the E2. What are the factors which favor E2? Mostly E2 reaction take place in one step. It's mean the abstraction of the base and the leaving of the nucleophile take place simultaneously. So, but in case of halides, the base can easily approach to tertiary halide because there is no hindrance for the base to abstract hydrogen from the tertiary halide. And second evidence and second factor which favor E2 is that a result of which by the attack the abstraction of hydrogen from the tertiary halide result a transition state which is more stable if the base abstract hydrogen from the secondary, and then in that case the transition state will become is a little bit less stable. In primary it will be further less stable. For example, here this is a tertiary halide, and the tertiary halide OH can easily abstract this hydrogen because there is no hindrance for this base. So it means that if we move from the primary to tertiary halide at the same time, the rate of E2 reaction will be also enhanced. The rate, if we plot the rate for E2 against the various carbocation, for primary carbocation the rate is also high as well as for the secondary, but for secondary it is a little bit it is more high, and for the tertiary it is much more high than the secondary and the tertiary one. Similarly, second one is the base. In case of E1 reaction, base has no effect. Both the concentration as well as the nature of the base has no effect because base is not involved in the rate determination step. So the strength as well as the concentration of the base has no effect on the E1 reaction. If the base uses a strong or the base uses a moderate or the base uses a weak, the rate will be remain the same in case of E1 reaction. But however, in E2, both the strength of the base as well as the concentration of the base favor the E2 reaction because it involved in the rate determination step. If it stronger, so it will abstract hydrogen very easily. If the concentration is more, it will also remove the hydrogen very easily. So it's mean if you plot the rate against the strength of the base, so for strong one the rate will be more compared to the moderate, and for the moderate the rate will be more compared to the weak one. For weak base the rate of E2 will be very less. So in summary, E1 reaction the strength of the base has no any effect, but for E2 both strength and concentration favor E2 mechanism. The third one is factor is the leaving group. As we know, we have mentioned in the previous lecture that leaving group may be excellent, may be good, may be bad. Excellent is that one if the negative charge which has no negative charge, for example water, alcohol, ammonia and primary amine. And if it's good, when negative charge is stabilized by halide, ion, halide, carboxylate, it will be bad if the negative charge is not stabilized, for example alkoxy ion and amide ion. So in case of E1, the leaving group should be at least excellent. If it is not excellent, so E1 reaction will be not take place. Still it will occur if the leaving group is good, but it will never occur when the leaving group is bad. For example, it has been shown here, when it's excellent the rate of E1 will be very high, but when it is good it still will follow E1, but the rate will be low. But when it is base, the rate will be very low, so it doesn't occur. Similarly, E2, if the living group for the E2, the living group should be at least good. It can also affect the rate of E2, but here the nature of the base and the living group has no so much great effect as in case of E1. For excellent, still the rate will be high, and for the good, the rate will be higher too. But for the weak one, for the bad one, the rate of E2 reaction will be very low. Third effect is that of the solvent. We know that solvent is of two types. One is the non-polar and the other is the polar. E2 reaction or elimination reaction is the polar reaction mechanism. It means heterolytically wasted, so mostly we use polar solvent for that. Polar solvent mainly of two types. One is the protic. Protic is that one in which hydrogen is bonded to a more electronegative atom, and other is the aprotic, where there is no hydrogen bonded to a more electronegative atom. So mostly the aprotic solvent will favor E2, just like is in SN2 reaction that we have mentioned in the previous lecture. And similarly in the E1 reaction also, the the E1 reaction is followed by a protic solvent, just like in SN2. If we use protic solvent, then it will follow E1 mechanism. If we use aprotic solvent, then it will follow E2, as just mentioned in the SN1 in SN2 reaction in detail. Because if we use aprotic solvent, then it will not interact with the base, so base will be free to abstract hydrogen. But if we use protic solvent, so in E1 reaction we can get a carbocation which is stabilized by a protic solvent. Due to this stability, so it will enhance the rate of E1 reaction. These are the references for further studies and from which I have taken this lecture. If you have any question about this lecture, then you can email me, or you can directly contact me through my phone number or WhatsApp. Thank you for watching this video.